This should be review. I'm hoping this is review. Most of you have worked with a metric system. Has anyone not worked with a metric system before? Okay, so we've all seen it. Okay. Oh, I remember what else I was going to pass out. Let me do that real quick. I'm going to pause this. All right, so I just passed out the periodic table with the conversion chart on the back. We need to be able to go back and forth. The first couple ones we are going to be using are going to be just metric conversions, but I'm going to show you, I'm going to show you how to do what's called the dimensional analysis, which is what they use in college. It's a way to keep track of the units on a thing, and when I have several conversions in a row, it's a way to keep track of them so I don't get screwed up. Okay, I know a lot of you know how to just move the decimal one way or the other way to convert from kilometers to meters and back and forth. But I want you to show me with dimensional analysis how to do it. Okay, so there's ways to remember it. If you need that, great. You have a chart like this, probably not as big. There are ones that we use often in chemistry, and there's ones we don't use so much. So we do use giga, mega, kilo, the base unit, centi, milli, micro, nano, and pico are the most common ones that we use. Okay? All right, just for fun. Okay, here's the play. This is a good one for football day, right? Game day. Go out 10 meters, then cut to the left 5 meters. Meters, Jason, this is football. Everything in football is measured in yards. Look, in order for me to get the ball to you at the right place at the right time, I'm going to need to do a whole bunch of trajectory and motion calculations in my head. Trust me, it's a lot easier using the metric system. I'm telling you, you can't play football with meters. It's weird. Fine. Go out 10.936133 yards, then cut left 5.4680665 yards. Tell you what, let's stick with meters. Okay? So just that's why a lot of scientists have changed to meters, because it's just so much easier to work with, easier to convert. Okay, again, LO9 is Learning Objective 9, and this is what we're doing today. It's called dimensional analysis. You'll also hear me flip into a factor label. That's the same thing. They just have changed the name to dimensional analysis now. Okay, so what we're going to do is when you go to convert one thing to another, the first thing you need to do is write down your conversions. What things am I, what equalities do I have? So liters to milliliters, what's my biggest unit in that? Liters. So 1 liter, and you'll see me use a cursive L instead of the capital L, just because my L and my 2 sometimes look a lot alike, and I hate to be confused. So I do that. Okay, how many milliliters is it equal to? 1 liter. 1,000. So that's my conversion. Okay, so I'm just going to show you real quick, simple. We're starting with 18 liters. This is what we call, sometimes in math they call it a T-chart. We call it dimensional analysis. You're not going to use an X for times. You're not going to use parentheses, because those get other meanings later, right? Because an X in math does not now denote timesing. It means an unknown, right? Okay, and parentheses, sometimes they get messed up and thought to be ones or something else, so that's why we don't use that. We use this T-chart. Basically, it means the same. The 18 is going to times whatever is in the top right, and it's going to be divided by what's ever below. When I do this, when I start with a dimensional analysis, usually the number is always only, I'll try that again. Usually, we only have the number in the upper left corner, but we can have units top and bottom on the left. Okay, so we're going to start with this one just first. I want to get rid of liters, so liters are going to go on the bottom. So I'm going to use my conversion factor here and put 1 liter on the bottom. It's equal to 1,000 milliliters, so I put that on the top. So I'm basically timesing 18 by 1, because they're equal to each other. Then I can cancel out liters. I times across, and I get my answer as 1,800 milliliters. And that's 18, did I put too many? I put too many. Oh, sorry. 18,000, yeah. I said the wrong thing, but I wrote the right thing. Okay, so on the next one, we're going to do the same thing. Again, there's 1 gram in 1,000 milligrams. And I'm just doing this so you can sort of see, I can set up the fraction any way I need to if I know it's an equality, because it's like timesing it by 1. So So I take 450 milligrams. Now my quality, I want to get rid of milligrams, so this time the 1,000 goes on the bottom with the unit milligram, and on top I put 1 gram. And again, milligrams is canceling out here, so I'll be left with grams. But this time I go 450 times 1 divided by 1,000, right? So then I'd end up with 0.450 grams, right? And most of you said, okay, I could do that in my head because I can move it, right? I'm just showing you the setup, so when we get a little bit harder here in a minute, you know what to do. All right, let's go on. So again, some easier ones. I want you to try and do it showing with dimensional analysis how to do it. Okay, so take this next couple minutes, do what I just did with these two. And you're already done. Just remember, don't use the x, because the x will be an unknown. Do the t-chart there instead. Good. And it should be a review for a lot of you. Mm-hmm. Well, we're going to be measuring a lot of different things, so yes. Okay, I'm going to have to find a place where you can go back. Okay, I'm going to put it up here. When you're ready, look up here to check and see if you got these right, okay? Okay, I'm going to take a little break and we're going to go back right by your table that shows you the different, middle of the last page. There's a little space off to the side. I'm going to give you some significant figure rules because I forgot to put them in your notes. And these are Mrs. Howe's sig figure rules. I hate really fancy words just because, so I just want, get the meat of the stuff, right? So there's 4 rules. So these are sig fig rules. I just want you to write them in there. So the first one's pretty easy. So these are significant. And you'll see me shortcutting significant and figures the way I just did. Okay, these are significant. Number 1. Numbers 1 through 9. So 1 page back from where we were just doing our calculations, there's a little bit of space on the right-hand side next to a table. Okay? Sorry, I didn't put these in. I should have put them in, but I didn't. So numbers 1 through 9 are always significant, anytime I see them. Okay? The second one is zeros that are sandwiched are significant. An example here would be like 101. That would be a total of 3 significant figures. Okay? Let's stand this up a little bit. The third rule, when they are significant, is still about zeros. Zeros that tell how big, should do a big B for big, or small. Nope, sorry, figged on that. That's the last one. Zeros that tell, you're okay if you put zeros that tell how well, there we go, something is measured. They count. The example would be like 101.0. That last 0 would be significant because I had measured to the 10th place. Okay, another example would be, so that here there would be 4 sig figs. Another example would be like this. This 0 would be significant because I measured to the last place, and everything in between would be significant because they're sandwiched between two things. So this would also be 4 sig figs. Okay? And the last one is a big not significant, is zeros that tell how big or small are not significant. Okay, that would be like if I had this number, it would only have one significant figure. Or if I had this number, this one would only have 2 significant figures, which would be this one and this one. The other zeros just tell me how small. Okay? And that's the only time I'm really going to hit significant figures. I've given you my rules. I'm going to remind you, because if you give me calculator throw up is what I call it, when you put a number in your calculator and you give me that whole thing, I'm going to get very not happy. Okay? I want you to be about close to what the significant figures are, if not. Okay? So that you don't tell me, yeah, all these are significant when I didn't measure that significantly. Okay? All right. So let's do these other calculations, if you haven't already. So calculate the number of milliliters in 4.5 cups of liquid. So this is where I need the calculation from the back of the periodic table. How many cups or milliliters are in a cup? Which one's bigger, cups or milliliters? Cups. So is there a calculation between a cup and a milliliter on the back? That would be English to metric. 236 milliliters. Okay, so then we're just going to start with what we're given, 4.5 cups. I want to get rid of cups, so 1 cup is going to go on the bottom. On the top is 236 milliliters. Cups is going to go out. We're going to divide by 1 so I can ignore that. Take this times this. Now, how many significant figures do I have here? 2. How many do I have here? So when I times or multiply or divide any significant numbers, I always end up with the least amount. So I can only report over here 2 significant figures. So somebody give me the calculator throw up. Give me the calculator throw up. 1,062. That's the calculator throw up, but I know I can only do 2. So what would I report? Good, I'm glad you said 1,100 and not 11. Why would I replace those with zeros? Placeholders, because 11 is not the same as 1062, right? But 1,100 is in the same magnitude as 1062. But I can't say that I measured to those places because I only have 2 sig figs. Okay? All right, so this would be my answer. Okay, let's look at the next one. What kind of things do I need to know for the next one? Okay, how many miles are equal to how many meters? So do you have that on the back of your periodic table? Oh, you have kilometers. How about if we go to kilometers, and then don't we know how many kilometers there are in a meter? Or how many meters? Which one? Kilometers? Try that again. Let's try. 1.609. My brain was listening, but my hand was not following. Okay, and then we know 1 kilometer is equal to 1,000 meters, right? So we're going to have more than one conversion here. So I start with my 6.7 miles. Okay, I'm going to use that first conversion. I want to get rid of miles, so 1 mile is going to go on the bottom. And on the top, I'm going to put 1.609 kilometers or kilometers. Miles go out. My next conversion is going to take me from kilometers to meters. So in 1 kilometer, there are 1,000 meters, and kilometers go out. The nice thing about this one is on the bottom there's all ones, so I can ignore the bottom and I just times to the top. And what, okay, now wait a minute, how many significant figures should I report? This one's a little tricky when I don't know for sure, because this one, these are considered, conversions are considered exact. I look back to how many I was given, and that's how many I should report. Okay? So I should report 2 significant figures. What's my answer when I get there? So this one's 11,000, which this is funny because I just picked numbers out of the sky, and I ended up with the same thing both times, close to it with 1 0 off. Okay, so then we look at the next one. Calculate the speed of a moving truck. Okay, we want to go to miles per hour, so I'm probably going to have to use these same, or meters per second to miles per hour. I'm going to have to use these same conversions, but I'm going to need one more. What other one am I going to need? Seconds to hours. So in 1 hour, there's how many seconds? 60 times 60, so what? 3,600, right? Is that right? Okay. So I need these conversions. Now this is one of the ones that I told you about. You're going to have a unit on the bottom. So 87 meters per second. So second goes on the bottom there. Well, since I've got just one thing to convert for seconds to get it to what it needs to be, I'm going to do that one first. So seconds is on the bottom. To get rid of seconds, I'm going to have to put it on the top. So 360, try that again. I wrote it right. 3,600 seconds on the top and 1 hour on the bottom. Seconds is out, and I've got hours where it needs to be. Then the next conversion is going to be changing the meters into kilometers and then into miles. So meters to kilometers, 1,000 meters, 1 kilometer. I want to make sure that it cancels out, and that unit is where the unit where I want it to be, not squared. Okay? And the last conversion, kilometers, 1.609 kilometers, and 1 mile. So kilometers cancel. Now, let me do a huge caution here. When you put it in your calculator, a lot of kids just times the top and then divide the bottom, but they forget one important thing. When they go to divide the bottom, they forget parentheses. Okay, so go ahead and plug that through and let's see what we got for an answer. How many significant figures should we report? 2. Good, because that's what we started with. If these are ever not on and the room is really nasty and hot, please turn them on. It's just I forgot to turn them on when I came in. Yes, ma'am.
So divided by parentheses 1, and then I times that.
Then you times through and then close parentheses, yep. So every time that I cross one of these lines right here, whether it be the top or the bottom, it's a times. So I'm going to times to the top, hit my divide, put my parentheses in, times to the bottom. We didn't have to do that up here because both of these were ones. Whenever you divide anything by 1, it's the same thing. But here we have something different. Anybody got the answer? Am I going to be speeding if I'm going that fast? $194.6, blah, blah, blah. Would be 190. 190, and what are my units? Miles per hour. So, he's going pretty fast. I would say he's speeding. Okay? I don't know. Get moving. I don't know. Put a jetpack on the back of him. I don't know. Okay. So do you see how this works, this factor label, or dimensional analysis? It's so that you keep track of the units. So don't forget the units when you give me the answer at the end. Okay? Units are really important, and you're going to be given points for units. All right, going on. Most of you know these shapes, I hope, from math. Okay, most of you can be able to find the area. I have given you the formula for the area because we're going to be using it in a density lab after the lab that we do this next time. A lot of the stuff that we're going to find density on has irregular shapes. And so what we need to do is find it by displacement. I'll show you in a couple things here. But you need to be able to find the area and the volume. So the outside area and the inside volume. I have given you the volume equations. If you don't remember the area equations, then you need to be looking those up. Okay? I've also given you the volume equations with diameter, because when you're in lab, you're measuring diameter. You're not measuring radius. Okay? So it's easier to do calculations with a diameter. Okay? All right. Enough said there. So let's do some problems. So if I have a circular petri dish with vertical sides, it has a radius of 7.5 centimeters. Now here I gave you radius instead of diameter after saying you're probably going to measure diameter in lab. Just go with me. So how would I find diameter from a radius? Times it by 2. Okay. So you want to fill it with a liquid medium to a depth of 2.5 centimeters. What volume in milliliters would be required? I don't want to waste chemical in lab, so I want to get about what I need to be able to pour it in there and get that. So we're going to figure that out. What about liters? What calculation am I going to use? What formula do I need? The cylinder. So what's a cylinder to get volume? Okay, so we're going to put this in. I'm going to change to blue so you guys don't get lost there. So pi, diameter would be 2 times 7.5, and I better not use that. I better use a, oh, come on, really? 2 times 7.50, and that's centimeters. And I'm going to square that times the height, 2.5 centimeters, divided by 4. What's my unit going to be? This is what I first do every single problem. Centimeters what? Nope. Cubed. So that's the first thing I do is figure out my unit. To be a volume, it needs to be centimeters cubed or milliliters. Now, 1 milliliter is equal to 1 centimeter cubed. Okay? So somebody plug that in. So we're going to go 2 times 7.5, then square it, then times it by 2.5 and times it by pi, and then divide that answer by 4. How many significant figures should I have?
2.
Okay, this one had 3. This one had 2. So I should have 2. Okay, give me the answer to 2 significant figures. 440? Okay, anybody disagree with that? We're going to be each other's checks, so if you're not getting it, milliliters and centimeters cubed are the same. Doesn't matter. And when I convert it to liters, it's going to be the same number of significant figures, so it doesn't matter. Okay, so that is equal to a milliliter. And now I don't have to use dimensional analysis just to convert this, right? I just showed you dimensional analysis so you could do it for the longer ones. How many liters would that be? Giovanni? That's how many milliliters. How many liters? Sounded like you said 440. Okay, so I just moved the decimals 3 places, or divide it by 1,000. Okay? All right, let's do this other one. We're going to see if we can consume this many microliters, microliter looks like that, of milk needs to be consumed in 1 day. Could it be done easily with lots of effort or not at all? So first thing I want to do is change it into liters, because I know what a 2-liter bottle looks like, right? I could probably consume a 2-liter bottle of something in 1 day. That's not too horrible. I'd be a little waterlogged, but I want to see what it is. So 76500 microliters. How many microliters are there in a liter? So 10 to the 6th. Should be 10 to the 6th, right? Microliters in 1 liter. Microliters go out. And what does that leave me for my answer here? Okay, so is this easily consumed with lots of effort or not at all able to be consumed? Easily. Okay, I think of a 2-liter bottle, then I go to a 1-liter bottle, and this is 0.075, so I'm looking like a teaspoon. I can do that easily. Okay. All right, then we're going to temperature scales real quickly. We use a lot of different temperature scales. Mostly we're using Celsius and Kelvin in lab. We still use Fahrenheit here in the US, and we need to know about what temperatures are what. To be able to go back and forth, Kelvin is degrees C plus 273.15. Fahrenheit, if you look on the back of your table, there should be a conversion between Fahrenheit and Celsius. And I believe Fahrenheit is equal to 1.8 degrees Celsius minus, is it minus 32 or plus 32? I think it's minus, right? Is it plus? Plus, it's plus, because Celsius is minus. Okay, so Celsius, to go back and forth here, is going to be Fahrenheit minus 32 divided by 1.8. So we need to be able to go back and forth between them. Notice Kelvin is the only one, I should have put the degree sign there, that does not have a degree sign. It's an absolute scale. Now we measure in Celsius in lab, but when we're doing calculations, we don't want zeros on the bottom of calculations because then it's undefined. We don't want negatives because then that skews the result and we end up with a parabola kind of result instead of a straight line that we can get an easy slope from. Okay, so let's do this. What temperature of 77 degrees Fahrenheit is measured would equal Celsius and Kelvin? To me, that's a little hot. I like it around 70, so I like it around 20 degrees Celsius. So let's see if we can convert this. So if we wanted to convert this to Celsius, we would take Celsius is equal to 77 minus 32 divided by 1.8. What do we get? $21.68. So 22 degrees Celsius because we only had 2 sig figs. Okay, did everybody follow that? So all I did is take 77 minus 32 divided by 1.8. So I plugged it into this equation. 25, okay, we got the wrong number. That's why everybody's shaking their head. I'm just going by what you guys are telling me. So if it's wrong, please let me know. Okay, so then all I have to do is add to that 273.15 to equal Celsius, or to Kelvin, which would be 298 Kelvin, right? Wait a minute, you said 2 sig figs. How come you're giving me 3? Guess what? There's a different rule for adding and subtracting. This is adding and subtracting. So when I add and subtract, I just go back to elementary school. Remember when in elementary school you had to line up the decimal before you added or subtract any number? That's what you're doing here. So when I line up the decimal here, 273.15, they both have a common number to the ones place. So I can report to the ones place. So when I add or subtract, I report to the last number they have in common. Okay, if it's a really big number and I have zeros on this side, then I'm going to put zeros to make sure it's that big number still. Okay? All right, let's go to the next one. We're going to be working with energy units also. And with energy units, they are derived units, and we're going to be putting them in our analysis in our lab. Analysis will include anything I have to add, subtract, multiply, or divide, so any calculation. So if I just wrote it down in lab, it's data. But if I do any kind of calculation to get it, add, subtract, multiply, divide, it is analysis. Okay? If I do any graph, it's an analysis. My conclusion, I really was sort of pumping you for conclusion at the beginning of the year to see how well you could write 5 sentences on something that was so easy you wanted to just, come on, Mrs. Howell, really? What I want you to do with conclusion is take everything you got in data, everything you got in an analysis, and basically like in a 5-paragraph essay, that last paragraph that you do, it summarizes everything and brings it back together. So in the beginning, I hypothesized this. We went through and we got this data. When it was went through analysis, we got this. And because of that, this is what I believe now. Okay? So we want that process in your conclusion. Okay? All right, so let's talk about joules. And I know this is little, so I'm going to rewrite it. So 1 joule is equal to a kilogram times meter squared divided by seconds squared. This is the SI unit for energy. Most of you are more aware of calories with a big C. A big C is equal, one big C is equal to 1,000 little c calories, which is what we do in lab. This is what we call a nutritional calorie. Nutritional, okay? I'm having problems with spelling on the board. And that's what we see on the sides of the food labels, okay? This is a nutritional calorie. So calorie in lab, how do these two relate? 1 calorie in lab is equal to 4.184 joules. Okay? So you need to be able to go back and forth with them. Table 1.3 on page 18 in your book or on the back of your periodic table will help you with dimensional analysis using units of energy. Okay? Now, I know it says more examples. We're going to stop right here so we can go to lab. Yes? To energize what? A lot. Well, if you think about it, our calories are usually written in kilocalories. So what does nutritional people in here, how many calories do you want a day? 1,400 to 1,000. Okay. Times that by 1,000, times it by 4, and that'll tell you how many joules. Then divide it by 1,000, get to kilojoules. So that's a lot. Okay. Basically, take your kilocalories times them by 4, actually, and then you'll have joules. All right. So let's go through this lab real quickly. You have about 25 minutes. So let's look at your paper real quick. There are 3 different areas. Across over here is the measurement of mass part. Back there is the measurement of liquid part towards the door. Up here are the rulers. You'll need 3, one that has centimeter marks, one that has no marks, and one that has millimeter marks to do the measurement part. Okay? There are several places that you need to do measurements. Now, I'm still going to break you into groups of 4. Sorry, 4. Changed my mind. Okay, so your group of 4 is what you're going to do these in. I'm going to tell you where to go. Okay, so weights, measure, liquids. Okay, you need to do all 3. So once you get done with your area, I want you to rotate around the room like this. Okay? So we're not all ending up with one place left that we all need to do. All right, so as soon as I tell you, you can go and move. Weights, measure, volume. Weights, measure, volume. Weights, measure, volume. Move. Time is yours. It should be taped into your lab. We'll have some time to finish it next time. But it should be taped into your lab too after your last lab. So, is this your?
That's the one I just did.
Okay, and that's the 2 pages you need, so you're going to need to tape it here. Okay. And then, yep, and then you can measure and actually put the numbers here and then use those to transfer to your data table. Okay.
Well, I have.
Good, awesome. Just go ahead and tape it there, and then you're going to start your next lab on the next page. Okay. You're welcome.
You have all three?
Yes. You need 3. So there's your 3 rulers you need. And what do you guys need? You need.
Or all four?
Oh, you're all 4 in the same group. Okay.
Where is the measuring one?
So it'll tell you what to do underneath
Okay.
your lengths. So here's another 3, and here's another 3. So are you guys another group?
Well, we need the other paper, right?
Yes, the other paper, this paper.
Oh, okay.
It'll tell you what you measure. So you guys the other measure group? There's your 3 rulers. And then you'll measure what it tells you on the front page.